All right, welcome back. We are game 3001. That's Artificial Intelligence for Games in the winter 2022 semester at George Brown, and it's week 3, part 1 of our broadcast and time together session. It's the first lecture that we're doing this week, and then we're going to be doing our labs on Thursday as normal. Let's continue with what's going on now. So let's talk about dynamic steering behaviors this week. So last week, where we left off, we talked about kinematic steering behaviors. And can anyone remember what was the difference we talked about briefly about kinematic steering behaviors and dynamic steering behaviors? Anybody? Kinematic versus dynamic. What was that slide that we talked about? It was like one slide, a deal. Anybody can remember? Kinematic can move, yeah, both can move, yeah. But what is the difference between one type of movement and the other? Kinematic is static, okay. Aiden says by dynamics, it's completely rigid. Nope, nope, not exactly. Keep going. Anyone else have another thought on what the difference is between dynamic and kinematic? We talked about there's two things that are different. Christian says kinematic is abrupt. Kinematic goes one speed. Yes, Trevor, I like that. You're close. And here we go. Simon's got it. Dynamic has acceleration and deceleration, and kinematic does not. Kinematic, and we kind of said static speed as well. People said that. So that's the difference in many ways between kinematic and dynamic, but there's more algorithm overhead involved in dynamic steering behaviors. We're going to be talking about those today. Compared to kinematic, realistic physics. It's not really related to physics, it's related to movement aided. All right, so that's what we're talking about. So last week we started also lab 2. Lab 2, we talked about making a game object in the play scene, and some of you had a lot of difficulty. I ran a little bit of a challenge in my labs, which was, can you make a game object appear in the scene? What are the challenges around it? What kind of challenge did you guys have making the game object appear in the scene? Do you guys remember what the problem was? There was one major problem on the lab side. Okay, Ethan says the includes. Yep, but what caused the includes? There we go. Lucas has got it. Where to put the files. Files got to put in the SRC folder. And that's a key learning. If you guys don't get that now at the beginning with lab 2, then when you start working on your assignment, you'll be like really messed up. You're like, I don't know why, but things don't connect. I can't make an object. The includes don't work. I can't reference other things like the texture manager and so on, because it has to be in the SRC folder. So this is kind of the output from last week, as well as in my labs, we also talked about 2D collision detection. I put up a little bit of an image on some standard 2D collision detection stuff, line, circle. We didn't really cover, but we did cover circle. We also covered circle ABB and ABB, kind of the standard stuff that you've seen in fundamentals, plus a little bit more. All right, so that's kind of something we did. We didn't get to start the seek algorithm, and that's kind of what we're going to be doing this week. And we're also going to be implementing something called look where you're going, which is an orientation algorithm that's going to help us. All right, so just to look ahead, week 4, it's coming up. Next week, assignment 1 will be due at the end of the week, and assignment 2 will be assigned. And then, of course, there'll be a lab that we're going to be working on. Lab 3 is going to be beginning obstacle avoidance and implementing primitive raycasting. This lab is critical to you getting your assignment 1 completed properly, and to kind of meet the obstacle avoidance requirements in your assignment 1. Okay, so please make sure. I mean, all the labs are critical because they're all worth 4%. But at the end of the day, this one is super critical because without this, then you won't be able to really understand obstacle avoidance and how to do it. All right, so that's happening next week. Looking further ahead, we're getting into pathfinding after next week. So this next week is the last lecture when it comes to dynamic steering behavior. We're going to talk briefly about path following and separation and collision. We're going to be more talking about avoidance, obstacle avoidance, and flocking. So we're going to bring some of that information into next week's lecture. Again, we're going to kind of review some of those things again, but mostly flocking and what that looks like starting next week. All right, let's move back into just a brief overview. Again, we talked last week about seek, flee, arrive, and wander. We did the first part of Lab 2. And this week, we're going to do the second part of Lab 2, and talk about dynamic steering behaviors. And again, just a reminder, assignment 1 is due week 4 at midnight. That's next week at midnight. For Lab 2, the completed Lab 2, which is due this Sunday at midnight, the lab report is required and a short video is required. It's an individual submission. Some people did not submit your Lab 1, and that's okay. You still have enough opportunity, if you will, because remember, we're not using every single lab. I think it's the best out of 14 possible labs. I think we're taking the best 12. So I think you're still okay if you miss 1 or 2 labs. Let's move on. So let's talk about steering behaviors a little bit, and let's talk about dynamic steering behaviors again. So again, it extends basic movement that we've talked about before, but we're adding things like velocity, rotation, acceleration, and deceleration, like we talked about before. Okay, and the question I asked you at the beginning of this lecture. And we're also going to be discussing next week something called flocking behavior. And what are flocks? Think about them as flocks of birds. We're going to talk about them. Actually, we're going to call them boids. So we're going to be talking about that. So this is kind of like the first part of our dynamic steering behaviors conversation. One thing we're going to be doing with dynamic steering behaviors is doing something called variable matching. Okay, this is kind of a key thing where we match either orientation and or velocity, right, of the target. So we have an autonomous character and it has to kind of point at the target. That's your orientation. Or we have to match velocities because I want to evade or pursue. That's a different kind of variation of flee and seek, right? So respectively. And so those are the kind of things that help us with variable matching. And variable matching means that we want to, there's certain things that can conflict as well with variable matching. One of them is if I want to try and match both my location and my velocity. That's very difficult to do. One thing that we're going to be doing is we're going to use variable matching combined with different kind of behaviors, and we're going to combine them together in order for us to create new interesting behaviors. Let's talk more about dynamic steering behaviors and the difference. Again, we started with seek and flee last week, and we started talking about how seek and flee was very static. We have, kind of a maximum speed. The character always is going at the maximum speed. So in that way, some people are saying when I think someone earlier said static. I think I'm just looking at the chat here, right? So Simon said originally kinematic is a static speed, and then that was a good observation. Then later Simon was saying today, just in our chat, that dynamic has acceleration and deceleration. So this is a good way of taking a look at a high level of what seek is and what flee is. So if this is the agent, the autonomous agent or autonomous character, we have, let's suppose they're going this way, right? So that's the current velocity. I'm just going to zoom in here so you guys can see it a little better. So here's the current velocity. I'm going this way, and this is where I want to go to seek the target. So then the steering algorithm is going to steer me back where I want to go, right? So I can kind of reach the target. That's kind of what seek does in a nutshell. And flee is the other way, right? So again, my desired velocity, maybe I'm going this way and the target is coming at me. The desired velocity is over here and my steering is going to be in this direction. Basically what you're doing is you're doing vector addition to get to have that happen. Again, take a look at these lines as vectors where we have kind of a direction and a magnitude, where the magnitude is my velocity. So here's my velocity. And now you have a new magnitude, a new vector that we're adding up to this one, let's say, for seek. And then we're going to get a brand new vector that's going to go in the direction that we're looking at. So that's pretty cool in terms of how it works. It's kind of straightforward for seek and flee. Sometimes seek is also called chase. And what we try and do, here's the variable matching piece. We want to try and match the position of the target. That's variable matching. I have a position of my agent, and I have the position of the target. And then what I want to do is match the position Um, and however, right now it's starting to use acceleration. So we're going to speed up to the maximum speed. That's the right way of doing it with dynamic seek. And then as soon as we reach maximum speed, it's going to overshoot the target. It's still going to overshoot the target. It's not going to slow down, even though we would like to. And we're thinking about arrival from last week, right? We're going to continue seek by itself, just overshoots the target at maximum speed, but it goes in the direction of the target itself, okay? And I've added some additional pseudocode in here. So again, it's kind of hard to see, but I'll kind of zoom in here so you can see it. So example would be, I have my desired velocity. And remember we talked about this as the current position minus the target position minus the current position. This should be target position here. And then the distance is whatever my desired velocity is. It's still a vector quantity. And that's the magnitude. That's the distance we want to go. And then we want to do normalization. And we talked about what normalization is. We want to make it so that we have a unit vector of size 1 times maximum velocity. We did that last week. We did a kind of an exercise on our little whiteboard where we kind of talked about what a normalized vector is, or a vector with the size of 1. That's what we talked about. So then steering, if we look at that thing, that's the desired velocity. Remember, with this, so a vector with the size of 1, almost like the direction we want to go in, right? Times the velocity, the maximum speed, if you will. And so steering is the desired velocity minus the current velocity. So remember, velocities are vectors. So where am I currently heading? Where do I want to go, right? That's the steering. That's where that's the output. All right, that's how I'm going to turn. Right now, this is immediate. If I was to do this, I would turn right away. And what we can implement here is a turn rate, right, to make me smoothly go that way, as opposed to immediately steer in that direction. If I immediately steer, that's more kinematic. If I accelerate or have a angular momentum, angular acceleration to get there, that's dynamic. Okay. So if we continue talking about seek and flee, flee then is just like a dynamic flee, right, is just the opposite of seek, where now we just invert the target position, right? So instead of like the target position minus the current position, which is the character position, you can do it the other way around. And now you have the direction where you want to go. And this is what it would look like for the flee path, all right, as an example. So if this is the target, okay, and let's just mark that again. So let's put a target there. And let's see if we can use a better font, because that's an ugly font. We'll use like the same font kind of family that we've been using before. So here's our target, right? And let's just go in there. So if this is the target then, right, and this is our autonomous character, so that's our agent. We also call the autonomous characters agents, right? And again, we can kind of use the same Arial font. There's our agent. So Arial font is there. And you can see that our agent starts off here. And if I'm seeking the target, then a dynamic seek will look kind of like this, right? So I'm kind of seeking this way. Why? Because I'm going to slowly change my direction. A kinematic seek, in contrast, right, would look very different. It would look more like a line that goes this way. So that's kind of a kinematic seek this way, right? Where a dynamic seek would kind of turn slowly. And we also talked about ways of implementing that with kinematic seek by using lerping. We talked about linear interpolation last week. And I think that was a really good exploration, because if you haven't heard about linear interpolation, it's a kind of a way to do things. We can also use clamping to clamp the maximum speed as well. Christian says, in this case, dynamic seek isn't realistic. Why would that be, Christian? No one would do this? Well, the thing is, remember that it's all depending on your speed. So imagine you have a thrust, right? And you can't slow down. You're going to kind of turn. You have a turn rate, and you're trying to seek the target, right? You're going to turn, and your turn rate will allow you to do this, right? So that's the kind of best thing you can do. And here's the flee path. Again, it's directly opposite of the target. So if this is the agent, we don't want to go there. We want to go this way. And we flee away from the target. Again, notice how we're smoothly changing our direction. Right. Seems like a spaceship trying to land. Kind of. It looks kind of like that. But remember, imagine if the target continues to move, it's going to continue to chase, which is what seek is, right? So what about the difference between seek and arrival? We talked about that. Seek will overshoot, whereas, just like our kinematic algorithm, we need to slow down to reach the target with arrive. And so again, think about this as, so here's the target. Let's just get some of those things there. I'm not sure why that disappeared from my PowerPoint, but whatever. So here's the agent. And so this is the agent. And just to be clear, this is the target. So here's the target for arrival, and here's the target for my seek path. Or so seek, as an example, what it'll try and do is continue to overshoot the target because it's going to keep our maximum velocity as much as possible. It's going to try and do whatever it's going to do, but there's no slowing down for seek. Arrival, what it does is it kind of does the exact same thing as the target, but slows down until it finally reaches the target. So the way arrive works then, it uses two radii. The arrival radius, right, as we saw in the kinematic example from last week, as well as a second radius, which is much larger and is used to begin slowing down. So here is, up here, the slowing radius. So when the agent hits that slowing radius, it starts slowing down until it reaches the target. A lot of times what we want to do is we want to calculate the ideal speed between the new radius, which is this one here, where character speed is maximum, and where the target is, where the speed should be 0. Okay, so think about doing that. How can we do that? We can use, again, we can decelerate. We can certainly do that, or we can even use a linear interpolation, where we kind of slow down from here to here based on the time, the t value that we're going to use to slow things down. Okay, so kind of an interesting way of doing things as well. Okay, so it's very similar, but we have two radii. And here's some example of pseudocode. I'm going to leave that for you to look at. And again, it's basically on, we want to kind of calculate the new desired velocity based on where we are today. So again, we start off with the desired velocity is equal to the target position minus the position. That gives us our entire magnitude. And once we get that, we want to get just the magnitude, which is the distance. What's the distance? And then what we can do is we can normalize. We're normalizing it, so we're getting a unit vector. So again, I want to put that down. So when we say the term normalize, right? And let's just reset this one. Reset. Undo. No, we don't want that. Let's grab this thing. Actually, I'll grab this thing. This is pretty cool. And so what we want to say then is normalize. The term normalize for us, when we hear normalization equals to, we want to convert, to a, kind of a vector with a length of 1, right? We can also call this the unit vector, That's what it is. So that's what normalization means. So whenever we normalize, if we have a total path, right? So the total length, because when we get this, if I take one vector and subtract it from another one, I'm not going to get a normalized direction. That's why we want to do this. We want to get the direction when we do this part thing, like target position minus position. We get kind of the whole thing. We get the whole magnitude. And normalization allows us to get the direction. So normalization enables us to get the direction or orientation of our target. Okay, so in other words, where do I need to look? That's what normalization enables us to do without having the entire length calculated in the vector. And that's really an important distinction between, kind of the normal way of doing things in this. Okay, so that's kind of one way of thinking about it. How about alignment? Aligning behavior, tries to match the orientation of the autonomous agent with that of the position of the target, ignoring its position and velocity. So position and velocity, we don't care, right? We just want to align, right? In many ways, alignment is related to something else. And this is, or the align behavior is related to this, which is alignment. Later on, we're going to learn next week about multiple agents and how they align with the direction of the leader. We kind of choose one agent to be the leader and we align with them. Think about these as a flock of agents. We're going to be talking about flocking next week. So that's what this is, right? So align is similar to arrive, right? In that it tries to reach a target orientation with zero rotation. That's important when it reaches the goal. So that's the way we want to do it. So we're aligning in this way. And it talks about here how we want to orient ourselves. And one thing we talked about is also last week, orientation is tricky because it wraps around every 2 pi radians, or if we think about this as 360 degrees. It wraps around, right? Keeps wrapping around 360 degrees. So we can't just subtract the target orientation from the character orientation to determine what the rotation is. We need from the result. We can't do that. It's more difficult to do, right? And that's a challenge for us, right? And that's why, by the way, notice it's all in radians because we want to convert from radians into degrees later, but radians are used from a computer perspective. So if this is the z-axis direction, or in this case for us, if we were looking from a top down, it might be the y-axis, right? The target is at 0.52 radians. Our current orientation is 1.05 radians. Then if we want to go this way, we need to rotate 6.27 radians, which is a wraparound, right? So that's kind of a weird way of thinking about it, and that can be a problem. So again, to find the direction of rotation, we subtract the character orientation. So that's where we're looking, the character is looking, right? As an example, from the target orientation, and then convert the result into a range minus, kind of a negative pi to pi radians, right? And we perform this conversion by adding or subtracting some multiple of 2 pi, which is 360 degrees, right? To bring the result into the given range. So some multiple of this in order for me to make a range of negative pi to pi radians, okay? And we can then use the converted value to control rotation, and the algorithm looks very similar to arrive, all right, which is very interesting. And one thing we're also going to be thinking about when it comes to align, and align is kind of a key way of thinking about things, is we want to smooth that out. We want to be able to align over time. We don't want to align immediately. If we align immediately, again, it would go back to kinematic motion. We want to kind of smoothly turn or have a turn rate. We're going to talk about that in a bit. Again, going back to variable matching, velocity matching, right? We could use velocity matching to match a target's velocity. And on its own, why would we want to do that, right? It's not that useful, but we can combine it with other behaviors, which we'll see later. And we've already talked about, in some ways, velocity matching with our arrival behavior. We're changing our velocity to whatever the target's velocity is in order for us to be right on top of it with arrive, right? Let's talk about something called the steering family tree. And again, the most basic behaviors are the ones that we can build upon, almost like a foundation. They're very basic, and we can kind of combine them with other behaviors to make them more interesting. So seek, flee, arrive, and align, things that we've talked about already, are kind of the foundational behaviors, all right? Seek, flee, arrive, align, right? Once we have those, then what we can do is we can create other behaviors from those. For example, pursue, which calculates a target for seek based on the motion of another target. So I want to pursue the target, and they're going to continue to move out of range. I want to cut them off at the pass. That's what pursue is. Collision avoidance, which we're going to talk about soon, which is when two objects are moving, directly at each other, kind of like playing chicken. They're kind of going to collide, right? What do? They want to try and avoid each other from, colliding with each other, because that's what AI units would do. They wouldn't just kind of rush at each other if they're going in opposite directions. And then wander, which is also another way of, kind of combining those other foundational behaviors, right? So again, let's take a look at that. So align. With alignment, we can do two things. We can use the face behavior, which is turning to face the the target. And this is kind of important when we want to fire our weapons and we have a firing arc. Let's talk about firing arc for a second and what that means. So I'm just going to bring up our little diagram again, and let's draw some simple stuff. In many games, what you have is you have something called a firing arc. So let's suppose this is your ship, right? I'm just using my simple drawing tools here. This is your ship, and this is the front of the ship. And let's suppose the target is over here, right? All right, there's the target. And let's suppose also that your firing arc is directly ahead, right? Within, kind of a cone of about 60 degrees, let's just say, right? So if you can have this firing arc, right? So starting from here and going to here, right? This idea of firing arc is how flexible your weapons are that are mounted on top of your ship, let's suppose, all right? And some games give you that thing. So if you make a front-mounted weapons that are mounted to the front, they only have a firing arc of, let's say, 60 degrees. I'm just roughing it, right? So by eye, 60 degrees. Then what we want to do is we want to be able to, let's suppose, rotate our ship, as an example, to face the target, to bring it into our firing arc. And once we can rotate to face the target, then we can fire. Otherwise, it's out of arc. It's out of our firing arc for this particular weapon. Let's say a front-mounted weapon. Of course, we can have weapons mounted on the sides, just like a battleship or an old pirate ship of the past, where you have some weapons mounted on one side and weapons mounted on the other side. They had different firing arcs. They only had like left side or right side. So these are the kind of firing arcs you can have. Front, right? And you can have some kind of side, like, right side or left side, right? You can also have rear, right? So we have a rear firing arc. Or you can have something like, the front half, right? So you have a weapon that can turn quite a bit, or the rear half, right? And you can, of course, have some kind of Gatling gun that fires in 360 degrees. Okay, so these are kind of very common firing arcs, right, as an example. And why I'm bringing them into you, because just to get you to understand, these could be some mechanics that that you might consider, right? And I'm bringing them to you because, hey, what if you make a game and you have a firing arc? Well, you need to face the target, and that's what we're saying here. We can face the target, and it's kind of brought from or derived from the align behavior, right? Seek and flee. You can, you can extend seek and flee to create pursue and evade, some kind of path following. We're going to talk about that briefly today. Collision avoidance and obstacle avoidance. There's a difference between the two. Collision avoidance is when, and this is, I'm going to ask you this question next week. Collision avoidance is when two objects are in motion, as an example, and they're trying to avoid colliding with one another. Okay, that's collision avoidance. Obstacle avoidance is when a single object, a single autonomous character, is trying to avoid an obstacle, something that's stationary, a wall, a block, a pillar, or something else like that. So that is part of your assignment 1, obstacle avoidance. I'm not getting you guys to do collision avoidance. That's really challenging. But we're going to definitely talk about obstacle avoidance, and you can kind of derive one from the other. Velocity matching allows us to kind of hit a rival, right? Because we want to try and slow down, and we kind of try and, if an object is moving, we can still do a rival. We can just match the target speed with our current speed at the end. So we can slow down, slow down, slow down until we're right on top of the target. And there's something called force field, which actually creates separation. We'll talk about separation and cohesion next week when it comes to flocking behavior. So pursue and evade. So when we think about a simple seek and how we can extend it and flee, right? Let's try and think about predictive behavior. So if we have a target character, and if I try and kind of move towards the target character, but it's moving. If I looked at its position, kind of last round, and this is the position that I want to go. And I say last round, I mean like this was last frame. So I want to kind of move over there, right? As an example. By the time I start moving in this direction, the target's going to be moved over here, right? So that is kind of inefficient. And so instead of seeking to the target where it was, and even try and seek to where it is, even if I try and seek to where it is right now, by the time I move towards there, as an example, where it is, it's gone, right? So it's better for us to seek, where it's going to be based on its current trajectory, all right, based on where it's heading, right? That is what pursue does. It kind of looks ahead and predicts where the target's going to be at some point in the future. Okay, kind of an interesting way of doing stuff. And that's why I think that pursuing is kind of like cutting you off at the pass. I'm going to make sure that, by the time you're going to get there, I predict where you're going to go, and I'm going to go in that direction. And depending on if you're in my firing arc, I might fire at you, right? So again, it kind of works out the distance between the autonomous character and the target, and works out how long it will take to get there at maximum speed. And it uses this time interval, so it calculates the time, as its prediction look ahead. So it says, okay, I want to calculate how long it's going to take me for me to get where calculate the target, keeping the target's rate of speed in mind. So imagine if somehow we had an inherent knowledge of our target's rate of speed. I can see, I have some kind of radar gun, and I can kind of know inherently how fast the target is moving, right? I can predict where it's going to be. And we can do that with our eyes too, just not as accurately, right? And so the new position is then used as the target of a standard seek. So now we seek to that new target where you're going to be compared to where you are right now, right? Because that's more accurate. And so pursue is a lot different than seek. So here's our agent. Here's our current target. We have a particular velocity for that target. And what we want to do is we want to seek in the direction of where it will be in time t, whatever that's going to be. So the final seek behavior is going to look like this, as opposed to kind of looking like this, which doesn't make any sense. Evade is the same thing as pursue, but in the opposite. So we're going to calculate, if the target is chasing us, we want to calculate where it's going to be, and we want to be where it's not going to be. So we're going to calculate a path where we're going to get out of its way as fast as possible. Okay? And I've given you some examples of some pseudocode for calculating, where I should be in the future position. What my future position is going to be basically on is whatever the current position is, plus the target's velocity, plus whatever the ahead calculation is, which is some kind of distance divided by 10. The distance between where I am right now divided by 10. So kind of where the distance of the target is going to be. I can kind of figure that out, how long it's going to take, and then I have an example of a future position. Face is, again, we just talked about it, is kind of related to align. And what we want to do is rotate towards the direction that we want to look at, if you will. And there's a couple ways of moving, right? We can, if I go back to my little thing here, if I want to move over here, and my firing arc, and I'm using this as a motivation. Let's suppose I want to get my target in my firing arc. So here's target, kind of out of arc, right? Which means that I can't fire at the target right now. And I haven't moved. There's two ways to do this. I can move first, right? And kind of move in a dynamic way and kind of get behind the target this way as the target's moving away. Or I can rotate first, then move. Okay, that's also possible. But again, you're going to rotate around your rate or your rotation rate. Let's call this a rotation rate, or let's call it turn rate. Turn rate, and the turn rate, might be the angular. We can also see that as the angular acceleration, whatever that maximum angular acceleration is. So most objects might have a turn rate, and the turn rate is going to influence how fast I'm going to turn to face the target. And so you can do it two ways, right? And you might say that, kind of moving your ship, as an example, or turning to face the target first before moving might be a better strategy than trying to move and then face the target at the same time. You should test it out. Really depends on the thrust, if you will, of the ship, how fast you're currently moving. If you're stationary already, right, then it makes sense to turn first, then move, right? But if you're already moving, then it makes sense to pursue, which means like trying to calculate where the target's going to be and then try and get your ship into firing arc. Okay. Nicholas has a question. Nicholas, sorry, you've had your hand up for a bit. What's your question, Nicholas? or is that question gone? Absolutely. Go ahead, talk. But remember, you're being recorded on YouTube. Go.
So I have a my question is something similar to like the target thing,
Uh-huh.
but so you know how in Assassin's Creed games, specifically Odyssey and maybe Valhalla, I can check in that,
Yep.
or the Far Cry games, when you're driving
Uh-huh.
and you go on like the autopilot route,
Yep.
right? Or like you're on the horse and you're going to a specific target. Would that be an example of the arrive or the what's it called pursue
It could be using
algorithm?
pursue. Yeah, it could be using pursue. And it's kind of a way of pathfinding. Yeah, so it's good observation. It could be using pursue. Absolutely. I have a feeling it's using more some kind of pathfinding algorithm, right? Path to the target or path following, like Raul says. But yeah, you could also use pursue based on the inherent knowledge of where the target is. Again, one thing to note, Nicholas, and this is good questions because you're trying to explore the algorithm. Yeah, as an example. Is how does your horse in let's say Odyssey or even Valhalla, if you're driving a vehicle or whatever, how does that object know inherently what the target's going to be? Well, you place the target. You as soon as you set the target up, it's kind of a quick way, and it's kind of, and I have to say this as well, it's non-diegetic, because in real life you wouldn't actually be able to seek to that target so accurately. But in game terms,
Yeah,
and from a game mechanic perspective, it makes it a little bit easier for us to get somewhere and actually get into the action. And so that's why I believe Ubisoft makes that a mechanic, so you can get into the action quicker, so that slogging across the world doesn't take forever. Do you know what I'm saying? Because you can make a lot of mistakes navigating around the world, right? So, but good
yeah.
observation. Thank you, Nicholas. All right. Yep.
Also,
Yep.
you also have the option to just follow the main road towards like any direction.
Which okay,
Would
so
that be like an algorithm where the program traces like essentially traces a line and it follows that line?
that could be path
That's right.
following, or it could be path finding. All right. So, example, if I have multiple roads as an example, and I want to get to a target, and there's many paths to get to the target, path finding will take the shortest path. Path
Mm-hmm.
following, right, as an example, would only follow the path that you're currently on and won't turn off the path, right? So kind of keep going. Might even overshoot the target, right? Um,
That generally does happen actually.
Sorry?
That generally does happen in
Yeah,
Assassin's Creed
exactly, exactly. So
movies.
path following and path finding are two different things, and we'll talk more about them and the differences between them not next week, but the week after. But thank you for
Okay.
those questions. All right, let's continue. So yeah, so that's facing. So facing is really cool because it changes our target orientation. As an example. Now, what's the difference between facing and look where you're going? Well, again, imagine going back to our little whiteboard. I have some thrust. Okay, so I have thrust that's going back this way, kind of behind my ship or my um, eh, let's suppose it's going, I have a vehicle or I have motion, and the thrust is kind of coming out of my ship this way, right? And I'm moving in this direction. Well, I can't just turn this way, right? I'm going to have some kind of turn rate, some kind of angular acceleration or maximum angular acceleration. But every frame, I'm going to keep stepping forward where in the direction that I'm currently facing, right? And a an inaccurate way of doing that would be to ignore facing whatsoever. So I want to move to that target. Well, then I don't change my facing and I move there, almost like side slipping. I slip to the left, right, as an example, or I slip to the right and don't change my direction at all, my facing. You can do that with some space games as well, where you can slip to the left or slip to the right. When I mean slipping is like you're going in this direction. If I need to go in that direction, I can kind of go this way or go this way. And that typically is okay depending on the type of ship. But imagine if you can't do that. All you can do is you can go in the direction that you're facing right now. Well, we need to use something called an algorithm called look where you're going. And what that means is you're going to use the align behavior and you're going to give the autonomous character an angular acceleration or a maximum turn rate. So a number of degrees maximum they can turn per frame or per time step, whatever the time step you're going to do, right? like the dodge mechanic in Halo Space Missions. Okay, we can look at it that way as well. But think about where I'm going to look where I'm going. I need to kind of turn, slowly, and turn around my path. This is going to make it so it's my motion is much more realistic than if I'm not looking where I'm going or I'm not aligned. Okay, let me give you an example. So let's suppose I have an object like this, right? It's a square and there's no facing whatsoever, right? But what if I give it a facing, right? So let's make it so that, kind of give it a facing like this way, right? And I want to seek the target, right? So let's do that. So we're going to kind of do one of these, and I'm just going to wrap my little shape up. So where if I'm not looking where I'm going, then when I seek the target, I'm just going to do this, doop, from here to there, like that, okay? But if I'm looking where I'm going, I'm going to move up first, change the direction a little bit, move in that direction, change the direction a little bit more, move in that direction, change the little direction a little more, and keep doing that until, right, I'm closer and closer to the target based on when I look at the target, right? And, whatever my turn rate's going to be. And this is the idea of look where you're going. When I'm finally meeting the target, every time step, right, based on my current direction and my velocity, and then I move in the direction of the target. Once I have the target, then it's no problem. Every frame, I can move in the direction that it's looking. And I'm sorry about the weird drawing because that's also affecting my movement, but that's kind of the way it works. So that motion that we saw there from here to there, that's look where you're going compared to if I'm, kind of moving and don't care about that direction. Like again, I'm just moving this way. So it's side slipping in many ways, and that kind of doesn't look realistic. To have an object do that kind of motion like that doesn't look right. Okay, but that is also very common, and a good way of the reason why that's okay is for particles. Particles don't need to have a facing, if you will. If I have a particle system, I have smoke, and I want it to go sucked into a hole or something like that, or a target for smoke or some kind of particle, that's okay. But if I have a missile, the missile should basically look like it's facing the target when it's moving, right? Because that won't look realistic if the missile does, what I said, which is, this. Missiles don't do this, all right? That doesn't happen. Missiles kind of keep in mind the thrust that they have, and that wherever the thrust is pushing them, that's in the direction that they're going to go to make it look more realistic. So that is look where you're going, and we have to keep in mind those two things. We have to use align behavior, which is kind of like face, and we have to turn in that direction. We have to use some kind of angular acceleration or a turn rate, a maximum turn rate per frame or per time step to change the facing, and then apply acceleration. So the steps are kind of like this. The steps are, so move, and then turn, and then move, and then turn, and then move, and so on, and repeat until you're facing the target, right? Until you face the target, and then just move afterwards, right? So that's what we want to do. It's kind of move and then turn and move and then turn and keep moving and turning until we do that. And that's the time step that we're looking at, right? Because those are the steps, right, that we want to accomplish, right? So if that's it, we kind of gradually get there, right? It makes it more natural. The experience for the player looks, a little better when the enemy agent's turning towards you. Because otherwise, imagine if the enemy's pursuing you, you're the target, and somehow they're just at you. They're, right, behind you, and they don't have to turn, and they don't have to worry about their maximum speed and so on. One other way to do it, of course, is to slow down before you change direction, which is also a tactic. So I want to slow down, then turn, then move, right? That is definitely an option instead of this kind of action. And this is kind of like an action sequence, if you will, right? Let's look at this as an action sequence. So here's an possible action sequence, right? Where, I have my enemy that's pursuing, do this. Move, turn, move, turn, move, turn. And the turn will be X number of degrees every time step. And by the way, please don't do this turn rate every frame. Remember I said time step. If once you start thinking about it frame by frame, and if I've got 60 frames per second, it's going to look immediate. It's going to look like it's going to snap from where I'm looking to where I need to go. So give it a turn rate over several frames. Okay, something like I can turn, 5 degrees every 20 frames. Okay, that kind of stuff. You have to make that turn rate, and you need to play with this number until it looks natural. And we can play with that. We can put the numbers into IMGUI, and to kind of kind of test out what looks right for our character to move. Okay, so that's look where you're going, and I gave you a bit of an algorithm to look at. Wander, it's different than kinematic wander. Kinematic wander kind of like is a little bit more jagged. We can smooth it out by using some kind of linear interpolation, but really we get a random, kind of direction that we want to move in. With dynamic wander, we have a circle, a target, and we're going to get kind of a random position along the radius of the circle, right, depending on where that is, and that's how we're going to do our dynamic wander. And we're going to change that again every certain time step. So we're not going to do that, every frame. We're probably going to have a delay or some kind of decay, right? And it's going to act like it says, like a carrot on a string. So here's the carrot, we want to move there. And so what we're going to do is gradually move there by using look where you're going, and orientation changes over time using that angular acceleration to move from where we're looking, their current orientation, to where we want to be, wherever the new wander target's going to be. We can seek to that target, and we're going to use that look where you're going orientation. So again, we have our target, and we have, this is kind of kinematic, we just seek to the target, right? Whereas in dynamic, we have a random area in kind of like a circle that's in front of the character in order for us to wander in that direction. That's kind of what we're wandering is different. Path following is something else that we're going to talk about in more detail next week, especially for voids, like for these flux, as an example. I want to kind of follow along a path. And we can create something like a spline, which is this like, path that looks like this, or we can also use a series of line segments, right, to kind of, accomplish path following. So if I use a spline, then what we want to do is we want to maintain some kind of minimum distance, as an example, away from the path. Okay, that's what we want to do. So we can kind of smoothly path follow. And sometimes that minimum distance will be either on one side of the path or the other. It doesn't mean that it has to be always, on the path. And you know why? Because of our thrust, because of our maximum speed. Sometimes our maximum speed, we're going to seek to that new position. So example, this is the first position we're going to seek to. And sometimes maximum speed will make us go in this direction and change directions so we can go back to this direction, change directions so we can go back to this direction. And we're going to do that based on our turn rate. Okay, so we're going to try and path follow as best as we can. Again, the process looks like this. 1, the current autonomous character position is mapped to the nearest point along the path. What's that nearest point, right? And 2, a target is selected which is further along the path than the map point by a fixed distance. So I want to get to the next point, as an example. And then we seek to that particular path. And it kind of looks like this. So this is our seek output. So here's where I am right now, nearest point on the path. And this is where I want to be, and I seek to that position, right? Now, is it going to look as natural and smooth as this? Depending on how many target points you have, how far ahead you look. The farther ahead you look, the more jagged it's going to look. The closer ahead you look, the smoother your path following is going to be, right? And you can talk about things like, predicted future position based on on the path we want to go to. There's also some issues. What about if I have a path that goes like this as a spline, but the target's over here at the end, right? Do I want to really follow the spline and do a stupid move like this? Or do I want to turn rapidly as fast as possible, even maybe slowing down or using a rival behavior to get to that, to do velocity matching to kind of hit the target, right? So sometimes what happens is the autonomous agent, if it's using predictive path following, we're going to talk about that later, is kind of going to use a rival kind of behavior to move and velocity match with the target as opposed to go through the entire path, which makes no sense. There's different kind of path types. There's, again, line segments, right? So straight line segments, as well as splines, right? As an example. And they kind of look like this, right? So we kind of have our line segments, line segment, line segment, line segment, or a spline, right? Splines, again, more difficult to calculate. Line segments, super easy to make, right? And the effect, it might be good enough. It might be just as good. This might be just as good as this, okay? And why? Because when an autonomous agent is in motion, it's very difficult to detect this little hump. All right. It's almost impossible, right? And whereas this one it's much smoother and it's beautiful, but chances are you as a player will probably not be able to detect this unless the look ahead point is very, very small, right? Then you're going to see a jagged here and then a turn and then go here and then a turn and then a here and then a turn, abrupt turn. Whereas, using a spline as an example, you can get a smoother path. So it really depends on, again, the look ahead distance. And there's also problems with path following, okay, as an example. So remember, we want to get that closest point. Well, what's the closest point if the path kind of turns onto itself? And you may not think that this is even a thing, but actually it is. So I start here, and here's the closest point. I'm adhering to the path. And then I get to this point, and I'm like, okay, so where's the closest point? This one, this one, this one, especially if somehow my turn rate puts me in the middle, like this. That could be an issue. That could be a conflict with, the path. If I have multiple places that I can be that are the closest point. Let's talk about separation. So again, in crowd simulations, as an example, or when we're going to talk about flocking next week, right? Then separation is very, very important, right? Otherwise, what's going to end up happening is one autonomous agent is going to crash into the other one. So what we want to do is have some kind of minimum distance that will allow. And if one agent gets close enough to the other agent, each of the agents are going to try and separate from each other. Okay, this goes along with something called cohesion. In order for us to keep a group together, we're going to talk about cohesion more next week when it comes to flocking. But separation is really, really important, and some not just for crowd simulations, but think about things like if you have enemy kind of aliens. You have an alien destruction game, and you have enemy aliens. Do you really want those enemy aliens to cross over each other and overlap? That looks terrible, right? Or think about some kind of racing game, right? I have a racing game, and I want the autonomous agents, as best as they can, try and keep a separation from each other, right? If they crash into each other, they should take damage, right? In a racing simulation. And in the proper racing simulation, what are they going to do? That's path following. That's going back up to here. So imagine I have a path I want to follow in a race game, and I'm using, a spline of some kind, and I have multiple agents kind of running around the spline. Some have vehicles or loadouts that have better, angular acceleration capabilities, better tires, less slip. So maybe some kind of the friction, their tires are better than others, so they're not going to slide or skid as much. They have better braking, so they can decelerate really quickly, or they have really great acceleration. You can make a vehicle with a lot of different properties that can affect its capability or kind of probability to hit another one, right? Especially if there's multiple agents on the screen at the same time, and they're all AI. All of them are AI. They're all driving around a path, as an example, and they're all trying not to hit each other as much as possible. It might still happen because of the acceleration and all these other things we're talking about, right? And if they do, boom, they blow up. And if there's a big enough blow up, the other agents might fly into them too, right? And they can blow up. So that can really be interesting as well. So really interesting kind of behaviors. And it all comes down to this idea of separation. How can I separate? And again, how do I separate? Well, I detect, first of all, that there's another agent that's close to me. And then what I need to do is using my angular acceleration or turn rate, so number of degrees I'm going to rotate every time step, I'm going to try and use my thrust to move away, or I might decelerate a little bit, so cut my speed down or increase my speed so I can avoid a collision. Those are the kind of the things that you can do, right? And this decision making that we have to do for the agent that needs to separate from the other ones can be quite complex, right? Imagine if every single agent is trying to do the same thing. So if I put a separation algorithm here, and if it was only there, that'd be okay, but I have to put it everywhere. All these ones have to have the same separation algorithm, which means I'm going to be calculating the distance between objects somehow and say, oh, I don't want to collide. I want to avoid collision, right? And one of the key ways of doing that is separation. So again, we want to use evade behavior, and what we do is we momentarily get into evade mode, right? So where I predict that the agent is going to be, right? And I try and avoid going in that direction to avoid colliding, right? That's what I'm trying to do. And I have this thing called the separation strength, which, and I can use something called the inverse square law, which is a decay mechanism, and which is very common to kind of, depending on how far, the distance is from the other target, then what I can do is I can decrease my speed or increase my speed accordingly so that I can avoid the other target. So very complex. It could be very complex movement that we were planning out. But here's an example of linear separation. It looks something like this. So my strength, my calculation, is my maximum acceleration, how fast I can accelerate or decelerate. That's what this means. Remember, we also have that factor, an acceleration factor, multiplied by some kind of threshold minus the distance of the other object, right? And then divide that by the threshold. So this is a normalized value that I'm gonna kind of put together a strength value. Or I can use something called the inverse square law, which basically kind of calculates the distance squared, distance times distance, right? And I want to take the minimum value, that's the minimum thing, between some kind of k value, and the k constant can be set in a positive value. It controls how fast the separation strength decays with the distance, so some kind of value that is positive value, right? So I multiply that by the distance squared, and then I take the minimum value between that and my maximum acceleration, and that comes up with my new strength, the separation strength, which is really another way of saying how far do I want to move, side slip if I can, or change my acceleration value to that strength. So kind of an interesting way of doing it. And again, I put some pseudocode in there for you to look at. Collision avoidance. So we're talking about collision avoidance, right? And we kind of briefly discussed it earlier. So we said, what's the difference between a collision avoidance and obstacle avoidance, right? So collision avoidance, we start thinking about things like I have something in my cone of, kind of detection, if you will, and anything that's inside of this cone, if you will, then that's the character to avoid. So I have two characters. I have an autonomous character here and an autonomous character here, and they're in my cone of possibilities. I might collide with them. So what am I going to try and do? Avoid. That's what I'm going to try and do, right? Whereas this character is outside of my cone of detection or my cone of collision area, potential collision. So I'm going to ignore this character. And again, what we're going to use is separation behavior or evasion, right, in order for us to do that. So this cone in front of the character is, we can calculate that by looking at almost like a cone threshold, or we can kind of do a cone check by using something called the dot product. And again, you should know what a dot product is, but if you don't, we'll talk about it, kind of in lab. And in this case, direction is between the character and the potential collision. That's the direction, right? And the cone threshold value is the cosine of the cone half angle, whatever that cone is, right? As shown in the current slide, this one here, this last slide here, right? It's the half angle. And if there are several autonomous characters in the cone, then the behavior needs to avoid them all by using the average positions and speeds. So if I have an average position, I can kind of figure out where kind of a clump of enemies are and their average speeds, and I kind of calculate where I don't want to be based on where they are. So that's kind of collision avoidance. And again, imagine if both characters have that. So I have a, kind of a cone of collision, for one autonomous character and another one. Well, we know that this one is going to try and avoid this guy, and this guy is going to try and avoid this guy. So they're hopefully going to try and go in opposite directions. They want to kind of go this way. This guy's going to try and go this way, and this guy's going to evade and go this way, and they're going to avoid each other as much as possible. So this is a two in cone character who will not collide, right? But what about if I have something like this? So I don't have any character in there. I can't detect the other person's cone. That's not what I'm doing, right? But we're moving kind of in the same direction, kind of to a collision point, right? It might happen, right? So two out of cone characters who will collide. It's going to happen because we're moving in the same direction, right? So this is a problem when it comes to collision avoidance. And one of the things we can also do is use something called collision prediction, where again, it's kind of similar to a pursue or evade, where I kind of figure out what is the future position of another character, and what their heading is. So if their heading is putting us in danger, we know that we're going to be very close to colliding, so we start avoiding early, right? And this is a neat idea, but how do we do this? Well, we have to kind of put together a separation. So if the separation distance, if I'm getting closer to the character, as an example, I can detect the distance, and if I'm really close to the character, I start predicting where the other guy is going to go. By the way, both characters are doing the same thing, right? So they know that there's a chance they're going to collide, and they start veering off early. Okay, so that's kind of the way it can work. So that's collision avoidance. Collision avoidance are between two autonomous characters that are in motion, okay, typically. So again, example would be, I have two vehicles that are kind of going head on to each other, or they're kind of moving in the same direction, or going to end up somewhere in the same direction. They want to avoid a collision, and they're going to either use separation techniques of kind of an evade algorithm or something like that in order for them not to collide in the future. Or if they're heading at each other, there's going to be some kind of, and by the way, the cone of collision detection could also be expanded to be a circle. So I can say anything inside of my circle or my radius. I want to keep other enemies or other characters outside of my, my bubble, if you will. And I'm saying bubble now in COVID is actually quite a bad thing, but let's just say bubble. So you have these two bubbles, and we want to kind of avoid each other, keep out of each other's bubble. And so what we do is we avoid. We use a kind of a radius. That's another way of doing it to avoid collision as we're moving. Obstacle avoidance is different than collision avoidance, like we mentioned before, where you have an autonomous character and you have a bunch of stationary objects. And what you want to try and do is predict where you're going to be. You want to use separation from those objects as an example, but what you're doing, you need to kind of predict what's in front of you. And there's a bunch of ways to do that. We could definitely use, kind of a radius around an object to detect, where I'm going to end up. And if I'm inside of that radius, I want to kind of angle away from it. But look at this scenario where I have two radii. I'm going to kind of go this way, and then, I can't go here. I'm probably going to keep turning because I want to avoid this guy, and I'm okay on this side because I've got some minimum separation from this obstacle over here. And when I say obstacle, these are not moving. They're like pylons or some kind of other obstacles, and that you can put a radius around them, and then you can kind of set that character to avoid. But a lot of times we use, especially when it comes to a wall, I'm kind of heading towards a wall, right? I can use ray casting to kind of detect where I'm going to hit, right? This is where it's going to happen. So I can kind of ray cast. And ray cast is really just like I have a line. And let me just go back to here. So I have a line, and we talked about firing arc. I'm just going to erase this. Hopefully you guys get the idea of what firing arc is, right? So we don't care about firing arc right now. What we care about instead is if I'm, kind of moving my ship, and you have some kind of obstacle, right? So let's suppose I have an obstacle that's in the way. So let's just put an obstacle. Oops. Let's put an obstacle in the way, like some kind of block that it looks like this. And then maybe we can draw it with, the proper way of drawing it, Tom. Hey, there's an obstacle, right? So I want you to think about the character is moving towards this obstacle, and I want to avoid collision. Here's my obstacle. Obstacle is not moving. All right, so stationary or not moving. That's very important because people have this idea that obstacle avoidance and collision avoidance are the same. They're not, right? And that's the big difference between this, because we want to make sure that you understand the difference between one and the other, right? I'm just going to clear this up so that it doesn't confuse anybody when we're in the video. Okay, so we don't care about firing arcs right now. That was a nice idea. We don't care about this target that's out of arc, or whatever. We don't even care about this really weird house, which I made as a ship. What we really care about is this, all right? So it's the obstacle to avoid. So how do I do that? Well, I can have rays or line segments that start casting. So when I say casting, it means relative to the ship, right, or your autonomous character, I can cast a line, right, that's in front. So I can do something like, let's cast a ray that's in front, right? This is one thing I can do. This distance, the distance of the ray is important. Let's use a different color so we can kind of look at it as if almost like a debug ray that we're using in front of the character. So let's suppose I have a ray, and that's the first thing. So that's what it's casting. If I have a single ray, then when the kind of the ray starts colliding with the obstacle, then I know that I need to turn. Okay, that's the idea behind it. So one thing to note is we need to do different kinds of collision detection methods that we need. What are they? We need to do some kind of, we need to be able to do some kind of line circle check. Okay, that's also very common. The other one is a line check. So if I have two lines, that's also possible. The other one is a line AABB check. All right, so those are the three types that we can possibly think of right now that's really realistic for us. So circle, line, and AABB. All right, there's other shapes as well. Where line, I would say, is probably the fundamental piece to it all, right? And the reason why we're going to say line is the fundamental is because if you realize an AABB is just 4 lines, right? 4 lines. So let's do that. So when we think about this, those are the collision detect methods, and line is the way to go. Why? If I have a ray, and if this is a ray, right? And we'll put that ray in here, right? This is a ray. Then this ray, if this is the obstacle, this obstacle has a bounding area, and maybe this is bounded by this box, this line here. So we're going to do line collision detection. And let's see if I can do that by drawing my stuff in different ways. Let's try that again. So I want to kind of situate my object like so. All right, so let's suppose I have my object now and it kind of goes, and now my ray crosses the object. Then what do I want to start doing? I want to start turning in one way or the other. I want to move, and my ray's still crossing, kind of move, and my ray's still crossing, and it's not now. And then what happens is my ray's not crossing, but guess what? Bam, I hit this anyway. So that's kind of one of the disadvantages of having a single ray, as opposed to having multiple rays, which is also something we can do. So when I'm drawing multiple rays, I can draw rays that come out of the front. And this is just some techniques. So I have 3 rays, let's suppose. All right, something that looks like this, almost like that idea of a cone that we talked about earlier. So now that I have 3 rays, well, that makes it so that my collision might not happen. And we'll talk about this on the lecture slides too. So again, imagine if, let's try drawing that a little bit more closer to this so we don't include the other ones. Imagine if we have our ship, again, we have 3 rays now, and we're way back here, right, as an example. So we're coming forward, we're going in, we kind of hit this ray first, and now we decide which way we want to turn. One way or the other, doesn't matter. So we turn, all right? So then we move and we turn. Because remember, we want to kind of move along our turn radius, right? So turn, right? And look, we're going to keep turning because our ray is still colliding. And now there's a chance that we'll avoid collision. Yeah, that's how it can work. Okay, so we'll avoid collision using the triple ray system. And there's different configuration of rays that we're going to get back to in a bit. Let's take a look at some of those. So again, ray casting is pretty cool, but we need to know this, at least a line collision detection methodology for us to do that. And so here is a grazing a wall with a single ray, or we have an obstacle, we have a ray, it's not colliding, but we're going to graze the wall anyway because that single ray doesn't give us enough information in order for us to avoid the wall, right? And here's a triple ray cast. That's a little better. We know we need to turn more until none of the 3 rays are colliding, right? So how do we know which way to turn, right? If these 2 rays aren't colliding, but this ray is, we want to turn to the right. If it's the left ray, I want to turn in the opposite direction, right? That's the idea behind this, right? if it's the right ray that's colliding, but not these two rays, we want to turn in the opposite direction, the left side, as an example. And so the distance between these rays are also important. You can make these whiskers, if you will, the one on the right and the one on the left slightly shorter than the middle one, so you can decide which way to turn. Why not have a ray on each side of the edge? You certainly could, Christian, right? And the other question that Christian's asking is, do the rays have to come from the same point? No, there's different ray configurations we'll talk about right now, actually. So we can have parallel side rays. So we have, kind of rays that are just two rays on the side. You can have a central ray with short fixed length whiskers, and these fixed length whiskers can allow us to have a chance to move. And actually, if you think about whiskers, that idea of whiskers, that's how cats actually navigate tight spaces. They're using their whiskers like ray casting, right? Cats, mice, any of those kind of rodents, right? What they want to do, even anything that has hair or follicles in the front of their face, a lot of these animals use ray casting in the form of whiskers to kind of detect, can I fit my face in there? I don't want to smash my face. How do I do that? I have these whiskers, and that's how I can detect which way to turn. If I can detect that there's something rubbing against my whiskers without touching my face, right, then I'm going to turn my head the other way. Kind of interesting. And so there's also single, and there's other configurations that you can use as well. Using side rays are interesting. Side rays can be interesting in that for separation purposes, you can kind of cast a side ray. However, just to note, the more rays you cast per agent, remember, this is per autonomous character, that's that many more checks that you have to make, that many more computations you have to make every frame, right, to avoid collision detection or collision of with other obstacles, right? So if I have many, many more rays, they're more accurate, but more computationally expensive. And then again, we have to go back to that idea of what is good enough. What is a good enough amount of rays that we're going to cast from our character, and from which position, in order for us to have reasonable avoidance capabilities. There is some issues, all right? There are some issues we want to talk about with multiple rays. Let's say two rays, the corner trap, all right? So again, I want to move this way, but I'm going towards a corner. And you know what? Even if I move a little bit, I'm still going to, hit the corner of the object. That's a corner trap. That's something that we can do for multiple rays. So the left ray is hitting, as an example, which tell me to turn to the right, and I still might skim and, kind of brush the corner, because even if I turn and I turn enough so that this, kind of this ray isn't hitting, it may not be fast enough for me, depending on my speed, in order for me to avoid the obstacle. And so what we can do is we can project the volume. And a lot of times what this is called is we can use swept spheres. And we'll talk about that more in physics, where I take a volume, right, as an example, like a kind of whatever the boundary type or collision type that I want, collision shape. So in this case, let's suppose my collision shape was a circle, and I can project my collision shape forward, right, as an example here, and I can project what that's going to look like, almost like I have a circle that's in front of me. A circle that's in front of me. So what I could do, right, instead of using a ray by myself, and some students have done this in the past as well, is not just put rays, again, more complex, a few more calculations, but what you could do instead is use I'm just going to move this back a little bit so we can give ourselves a little bit more room to draw. But instead of that, use circles, right, at the edges of the rays, the whiskers. So here's a circle, let's suppose, and here's another circle, and then here's a third circle. And why the circles are really great is because there's a radius, and it almost takes up a lot of these things. So instead of using rays, you just project circles in front of you. Don't even think about rays. In front of you, there's these three circles, right? And if this circle is hit, then you start moving. And the great thing about a circle is this overlap circle and whatever the object is, right? That's one way of doing it. The other way of doing it is you project something in front of you. For example, if this is the size of your object, let's just use the proper thing, Tom. We project kind of the object in front of us, almost like in a band, like something that looks like this. That's also another option, right? So I'm kind of here. I know it's colliding. And because the object has the same width, whatever that object is, this AABB has the same width as my object, then when I'm moving, let's see what that looks like, right? If I was going to predict its motion, and I'm going to try and grab everything, right? Sure. So I'm moving and I collide. The only problem with this issue is which way do I turn, right? Whereas if I have two short whiskers, one on the left and one on the right, it can help me, but I can also turn in a random direction. It doesn't matter. Let's turn to the right. We're turning to the right. That's the random direction. And we're marching forward. We're still colliding. We turn to the right. We're marching forward. We're still colliding. Turn to the right. Again, we're still colliding. Take a look at my ship, though. Don't worry about the ray. Now we're not colliding, and my ship is going to make it through, right? So that's also another way of, kind of using collision avoidance or obstacle avoidance by using some kind of swept collision volume that's in front of you. And it could be something that looks like this. It could be accompanied by, multiples. All right. So example, we drew one, but what's wrong with drawing a bunch? So I have one that is drawn like this, at the edge. Again, you want to make it so that it is, here, and you have another one that is here, right? Again, you want to try and use the simplest shapes possible. So you want to use kind of like AABBs, and you have another one that's in front that kind of goes in front like this. And then you can use these three shapes, which are very close to each other, and they're kind of computationally less expensive than rays. Lots of ways of doing that. It's up to you. I'll leave it to you for your assignment 1. How are you going to do it? What would happen if only the middle line circle gets hit? Well, that's the problem. It would keep going. It would try and choose a direction to go in. And a lot of times, guys, what you could do is calculate the distance to the edges, right? So this is kind of understanding when I kind of cross over for here. If I have a line, and let's just get rid of the circles for a second. So no circles, right? And I go back to those whiskers, because this is kind of, we're going to teach you this method anyway, right? So let's kind of look at these methods where I have a bunch of whiskers, and like you said, I don't collide with the right or left, but I collide with this first, right? Once I overlap, right, for my object, once I have this overlap, it's a line-line collision detection, right? And I know two things: where the line begins, so let's call it A, and where the line ends, which is B. So there's A, part of my line segment. This is a line segment, right? And B. So, and we also have the point of collision, which is C, right? If we do some math, right? What's closer, B or A to C? If B is closer, we want to turn to the right. If A is closer, we want to turn to the left. That's a way of doing it as well, okay? So we can kind of detect those things as well. And depending on our collision detection algorithm we use, we can get this information. What is the closest point, A or B? If B is the closest point, we go in that direction. The other way of doing obstacle avoidance, which I've also seen, is creating nodes, obstacle avoidance nodes, that each obstacle is a smart obstacle. And let me draw those in a series of squares. All right, so let's suppose that I have an obstacle, that there are little nodes, almost like helper nodes, around the obstacle to help the ship avoid, right? Instead of using rays, I don't use rays at all. Instead, what I use is, I might use a central ray, right? And that's it. But I have a series of nodes, and I want to put them kind of at the corners first. So let's suppose I have a kind of a node at the corner, a node at the other corner, a node at kind of this corner. And these nodes have to be at a distance, minimum distance, so that the ship or the autonomous agent will not collide. There's no chances if I seek to this object, will I collide with this thing over here. That's the idea. And these positions, right, are ways of almost like navigational waypoints. All right, so again, if I only have a central ray, once I hit, depending on if A or B is closer, I start turning, and I can also calculate if I also give myself a node, so kind of a moving node. Here's the moving node. What's closer, this node or this node? If this node is closer, I seek to this one, right? And then I avoid. So that's another tricky, hacky way of doing it, right? Where each obstacle is a smart obstacle and might have one or more, kind of path nodes, right? Even something that looks like this, where you kind of seek to a path node to avoid colliding with it, right? And you could even have path nodes that are kind of further up, where I might have path nodes so you can avoid it from different directions. And again, it would be based on the minimum distance between the path node and this object here. But again, look at that complexity. Each obstacle takes care of, let's say, 6 or 8 different path nodes. And this is a way, once my central ray detects the object, then I go, okay, so what is the closest path node that'll avoid collision? Well, obviously not this one. This is kind of in my cone. Outside of my cone, the closest path node outside of my cone that can avoid collision. Well, how can I do that? Well, it's either this one or this one. Most likely it's going to be this one right here. And I'm going to move to kind of hit this one here. This is the one I want to go towards, as an example. Okay. And then from here, my next path node is going to be this one. And then my next path node is going to be this one. And I've avoided colliding. And now I can keep going. Right. And this is kind of a way of doing it. All right. Questions around some, kind of ideas around how we could do, kind of a obstacle avoidance. Questions around that? I know that there's a lot of different methodologies here, but using raycasting is really cool. And once we start thinking about raycasting, we can do a lot of things. I can create shadows in 2D. I can use it for collision detection, right? In physics, I can do it I can use it for many things. I can use it to see if I'm grounded, right? So again, imagine if I have some kind of platform, right? And you guys are making kind of platform games. Let's try and draw a platform, right? So, and I'm going to try and just do this for interest and for help, right? So you guys are having a platform and you have an autonomous character or some kind of, whether it's an enemy or even a character. And let's use an oval to kind of set up the character. So we'll kind of say the character looks kind of like this, like some kind of capsule, right? And then how do I detect if the character is grounded? Well, certainly I can use collision detection and overlapping, but that's kind of weird. But I can always use a ray to do that, right? So I kind of cast a ray from the center of the character down, right? And if the ray is good, as an example, directly below me, then I'm grounded, right? As an example, I can also use a second ray that kind of looks in front of me, right? And as I move around the platform, if I get to the edge of the platform, right, as an example, I can detect if there's ground ahead. If there's not, turn around and go the other way. And of course, the rays would flip. This ray would flip this way, right? So this is kind of a common methodology of using a character on a platform or with ray casting. So learning ray casting now is kind of a really great way of doing it. Nicholas says, wouldn't having the double side ray cast be the most efficient option unless the object is only between the two rays? Again, there's lots of tactics to use one of these things. It all comes down to performance and how you make these things work. Sometimes, remember, all of these things can be made to work depending on how you think about this. Even a single ray can be used to work, right? Example would be, if I'm going back to here, if I use a single ray, right, is immediately when my single ray, my center ray hits an object, I slow down. I cut my speed to half my speed or a quarter of my speed, as an example. And I decelerate, right, to quarter my speed. What does deceleration do for me? It enables me to use my angular acceleration or turn rate to avoid the obstacle easier. So even a single ray can be good if you combine it with, some kind of arrival or scaled speed, which is really, really cool, right? So lots of really great ways of doing that. Other question, Nicholas says, then if need be, you could have a third in the middle agent as well. Yeah, you could. You could have all kinds of stuff as well, but at the end of the day, it's really up to you how you want to set this up and what works for you. So like you said, parallel side rays might be good enough, or just whiskers like this. That might be good enough. Parallel side rays are great because they can avoid some of those issues that we talked about before. The problem with parallel side rays is, as we approach an object, and if they both hit at the same time, which way do you turn, right? So again, that's a challenge. Where if I have a center ray and I have two whiskers, even if they're shorter whiskers like this, you can have parallel side rays with a center longer ray, and then now you know which way to start turning, and you can use the secondary ray, the one on the right or the one on the left, to make sure that you miss. You kind of move out, and again, you can adjust your speed and all that kind of stuff, and turn more, as an example, as much as possible to avoid collision. All right, so those are the things we've talked about with obstacle avoidance. So this week's lab, things that we're going to be talking about this week. So there are two goals that we're going to do. One is let's implement seek behavior for this lab. How does seek work, right? And we're going to use that. Okay, I have the target. I know where the target is. The target's position. I know my position. I'm going to normalize my direction. I want to find the direction that I need to go in. What is my current direction, right? And what is the difference between where I'm looking and where I need to go, and how much can I turn this time step, whatever that time step is going to be, right? And then implementing look where you're going is part of that. Okay, so we're going to kind of do this together, right? So that way you have a look where you're going and seek behavior all at the same time. Okay, and Nicholas says, also, couldn't this be put into avoid collision for self-driving cars, this application? Yes, that's exactly what happens. Actually, with self-driving cars, we have a bunch of sensors, right? And we do collision avoidance. The problem with self-driving cars is that their sensors can get occluded or blocked, right? By things like snow, rain, dirt, those kind of things. So one of the biggest challenges we have is, I hate to say this and be Star Trek-like, but our sensor array on autonomous vehicles are still primitive, right? We would need more sensors, way more sensors, and especially in the snow and rain and dirt and all those kind of things in order for it to go. Or if we can't see, so all the sensors are occluded, some kind of superior global positioning system where we can get the global positioning of an object right down to the nearest centimeter, right? If we have that kind of fine-grained accuracy of a vehicle, then I can look at an object, and from some kind of global positioning system, satellite or whatever, and it could also be not a global positioning system based on a satellite, but maybe the ground itself. We've been talking about this for years, where you have your pavement, the things, or the cement that you're driving on the roadway. Maybe there's different layers in the road, and one of the layers could be a sensor that has nothing to do with snow, rain, or whatever. And what that would mean for us is to, when we're rebuilding our roads slowly, kind of implement a sensor system that can help guide cars, right, that are on top of it, so that we know we have more accurate positioning of where the car is going to be. Things like lane centering, especially in the snow and rain where we can't see, and all those kind of things. And the other thing that would really work great, Nicholas, in my opinion, is, and this is looking forward several years from now, where everybody is forced to use a self-driving vehicle. There is no more, you're not allowed to drive a manual vehicle, manually drive, because there's so many vehicles in the city. As you kind of enter the city limits, you switch to city traffic control, and city traffic control takes over your vehicle and then guides your vehicle to its destination, whatever that's going to be, right? You're saying lasers, infrared lasers predict, measure the distance of obstacles. You could, but again, lasers and any kind of sensor can be blocked. And that's the thing. How do we unblock sensors? Can we make sensors so that they defrost? Do we make sensors so that they're auto-cleaning? We need some way so the sensors aren't occluded. If the sensor's occluded somehow, and it could be sonar or LiDAR or some other thing in combination with all these things. And I know that a lot of autonomous vehicles use things like LiDAR in order for you to detect what's coming up. They kind of create a moving picture in 3 dimensions about what a vehicle is seeing, right? And then we come up with ethical issues. You have an object that comes into your path that you don't detect. What do? Kind of stuff, right? So, but again, sonar, any of those kind of things, sonar, lidar, radar, all those kind of mechanisms. The biggest problem is, what if it fails? So you have a sensing system and your sonar goes down. What do you do? Or lidar goes down, whatever it's going to be, right? How do you need to have a failsafe. So that means you have to have redundancy built in, right? Multiple sensor systems that are layered on top of each other in order for you to avoid losing sensor control. And if one of the sensors goes down, it kind of says, okay, you've got to take your car into the shop because it needs to have your sensors fixed. You know, what happens if you get into an accident somehow, or someone hits you? So you don't hit someone, someone hits you. That's also a risk, and they break a bunch of your sensors, right? Well, then your car is undrivable at that point, right? Because you've got a bunch of sensors that are broken, and you can't drive your autonomous vehicle anymore. That's a real issue, right? So again, these are some of, and there's a bunch more issues around autonomous driving, where Tesla's really pushing the envelope, where they want to have pure autonomous driving as soon as possible. Level 5 is what they call it, where you don't even have a steering wheel or pedals, and the whole car drives for you. Simon says, for the assignment 1, do we hand in as a group, or do we each hand in individual versions? Well, the first thing, Simon, is please join a group. So again, if I look at Blackboard Online, thank you for that question. If I look for users and groups, if I look at groups, we can see that there are several groups that have been created, right? I think it's something like 40, I think I made. And of these 40 groups, I have still some groups that are empty and some groups that are a group of 1. For example, group 18, that's a group of 1. Group 20, group 22, group 20. And there's some that are group of 0. So if you haven't joined a group, that's the first part. Once you're part of a group, any member of that group can submit, and they submit for everybody. All right, so that's the great thing about groups. Any other questions around assignment 1 before we move on? Nicholas says, sorry for the off-topic questions. I was in mechatronics prior to. Yeah, I love mechatronics. It's great. And, sensors are awesome. And like I said, they're amazing. It gives information to the autonomous agent. But how do we use those sensors so that they're accurate? And what about if we had, as an example, every car was autonomous, drove, it was an autonomous vehicle. What would that look like? It would change what we do today. It would change the way we operate today. It would change behavior for all of us, right? Simon says, and the presentation is also as a group. Yes. So you'd have a video presentation. But again, what I said in the video is use your best speaker. It doesn't have to be every single person. I mean, I recommend both people can participate, or 2 or 3 people. But if one person is really great at public speaking and you want to use that person to make the video, and as long as it meets the requirements, we're good to go. Okay. So again, if you haven't signed up for a group, I think this is a great segue to that. Sign up for a group today, right? You can't sign up for a group, you won't even be able to submit your stuff. Please don't ask me for extensions as we get forward. We have 4 weeks. We've given you 4 weeks to get this stuff. You can already have started. There's a lot of little things that you can do with no knowledge of AI, right? Like setting up your scene and all that stuff. We've done that from like lab 1. Lab 2, we've talked more about how to add different pieces, and also you should be experimenting with things like IMGUI for your properties and for your debugging values and all that stuff as well, right? So think about how to turn things off and turn things on with IMGUI. Experiment with that. You should be doing that with your application framework right now. Nicholas said, I had an idea to install electromagnet strips in roads. Yeah, that's what we're talking about. Similar to what maglev trains do. Yeah, it's something that's been discussed. There's a lot of papers. One thing to note, if you're interested in any of that stuff, is take a look at the current literature that's out there. So do a lit review, I think, is a great way of doing it, where you kind of look at the current literature, the current research that's been done out there on autonomous vehicles, and see what they're proposing. And a lot of those ideas have been implemented in some of the most modern vehicles that we have out there, the Tesla, the other vehicles that are coming out. Remember that we have a mandate by the year, if I'm not wrong, 2035, that manufacturers will only be manufacturing autonomous vehicles, something like that, 2035. And by 2050, they're going to basically make, gas-powered vehicles pretty much obsolete, right? So we have a lot of changes coming up. in front of us, and it's going to change the way we travel, change the way we communicate, and a bunch of other stuff. And it comes from artificial intelligence. These little things, pathfinding, path following, and collision avoidance and collision obstacle avoidance. All those things. Yeah. So it's really, really, really challenging. Get rid of gas power by 2035 is like it's an awesome goal. Is it possible by 2035? I'm not sure. It's political as well. Yeah. Christian says not attainable. I agree. I think it's going to be very challenging for us. And it's not because it's not attainable because it's not possible technologically. It's not possible politically, right? And that's a different discussion. Anyway, let's get back to this. I know it's off topic, but things we covered today and key points of things key takeaways that I want to discuss, right? The idea that you're going to be doing things like in your assignment 1, you're going to be working with seek and flee. So seek and flee are the easiest ones to do. Seek is the first thing we're going to be working on this week, how to seek to the target, and so on. Look where you're going is also something that is part of assignment 1, and it has to do with, it comes from the basics of alignment. How do I align my orientation or variable matching again? I want to match my orientation so that it's kind of looking at the target. And I want to do that in a time-stepped fashion. So I'm going to change my alignment or facing, right, step by step from one time step to the next. And I say time step as something that we're going to do. The whole steering tree family is important to know because mostly everything comes from alignment, seeking and fleeing, velocity matching, and separation. This should be actually reversed, right? Separation. Because at the end of the day, if I want to create a force field effect, then I want to use separation. Those kind of 4 basic things are the foundation for most of the other steering behaviors that we're going to be talking about coming forward, right? It's just the last names. Sorry, let's go back out here. For the zip file, do we do last name, first name, and so on? No, just last names is fine. Just exactly what Nicholas is saying. 2 last names. And so that's the stuff. Pursue and evade is something that makes more sense. It looks more natural. So that's something we have asked you to look at as well. The difference between pursue and evade and seek and flee. We're only asking for seeking and fleeing, but if you can do a pursuit and evasion, it's much better, right? I believe that's what we're doing. Facing again is how much we change, and look where you're going is based on kind of alignment and facing. And the look where you're going, we want to make sure that you have some kind of angular acceleration or turn rate assigned to your character. So that's something that we talked about today, just to sum up. Okay, we didn't care much about wander for this one or path following, but we do talk about the idea of separation and how separation can also lead us into the discussion about collision avoidance, and then further down, obstacle avoidance. And this obstacle avoidance, by selecting the right type of ray to cast in front of you, or to use some other kind of collision avoidance technique, whether you're using node-based collision detection or avoidance or whatever. The idea is that there's going to be some fundamental collision detection methods we need for ray casting, and the main one is line-line collision detection, which we'll talk about on Thursday. That's going to be a fundamental thing that we're going to be doing. Okay, so that's kind of a review, and that's it really for today. Any questions before we go for the day? I'm going to stop recording on YouTube. I know this can be complex, and for some of you, when we think about this, it's easy for you guys to understand the theory. But remember, taking it back down to the programming. Remember that difficulty you had just adding a game object? Absolutely. The recording is up online. As soon as I'm done, it's going to be available for you to view, Aiden, anytime you like. Okay. And remember, all the recordings are going to be up online for you to look at. They're already up online. If you look at last week's recordings and the week before that, if you missed something or if you want to go review something else again, from a theory perspective, they're there for you. Please take a look at them. I think one recording kind of feeds into the other one. All right, that's it for me, guys. I'm going to stop recording this and I'll take some questions related to your assignments or any other questions you might have. All right, and we're not on YouTube anymore. So